Hi folks, today we're going to discuss the article entitled Multilayer Feedforward Networks are Universal Approximators, where the lead author is Kurt Horneck. This is an article that was published in March of 1989 and has been cited over 27,000 times. To understand this article, it's necessary to develop some intuitions about data representation, and to do this, I'm going to draw from a book titled Deep Learning, where the lead author is Ian Goodfellow. I'm going to cite the following passage. Much as a Turing machine's memory needs to be able to store 0 or 1 states, we can build a universal function approximator from rectified linear functions. There's a traditional approach to data representation where the world is viewed as a collection of discrete true or false propositions. Data is stored as a collection of zeros or ones. And this representation requires high precision but does not generalize well. In contrast is the deep learning approach to data representation, where the world is viewed as a collection of continuous data approximations. Data is represented by an algorithm fitted to a probable distribution of the data, and precision is based upon need, and data can be generalized. I'm going to discuss these last 2 points during the course of this presentation. To more fully understand the traditional approach and its shortcomings, I'm going to cite a concept known as a non-distributed representation of data. So imagine you have a collection of poodle photos and a collection of cocker spaniel photos. And imagine that you add another photo, which happens to be of a poodle. That photo would, of course, be clustered and associated with the photos of poodles. Imagine you add yet another photo of a cocker spaniel. That photo would, of course, be associated with the collection of cocker spaniel photos. You could even draw a line between these two collections of photos such that poodles would be on one side of the line, cocker spaniels on the other, and that poodles could correspond to the value of 0, cocker spaniels could correspond to the value of 1. Now what happens if you introduce a photo of a cockadoodle? Where does it belong? Does it belong here? Does it belong there? An issue arises about where this photo of the cockadoodle should reside in this distribution of data. So to summarize the approach associated with the non-distributed representation of data, the approach is one where the closeness of an image to an existing classification is dispositive of the class to which the image belongs. Further, there's a concept of smoothness that's used as an underlying strategy for classifying an image. Smoothness being where you look to the proportionality of an image's similarity and differences with other images to make a classification decision. Now, problems with this approach are as follows. There's poor attribute generalization, namely that an image must have been observed before and must match the entire distribution of data for a class. So, for example, you could never identify a poodle, cocker spaniel, or cockadoodle as a dog, because while poodle, cocker spaniel, and cockadoodle and their associated data distributions can be captured, the concept of dog is really an abstraction. Further, there's the problem of oscillation, where insignificant changes to existing image could change a classification decision. Put another way, a cockadoodle could become a poodle or a cocker spaniel at a later point in time. An even bigger problem with the approach of non-distributed representations of data is the curse of dimensionality. The curse of dimensionality is defined as the number of possible distinct configurations of a set of variables increases exponentially as the number of variables increases. Well, what does this mean? Well, imagine again that we have our collection of poodle images and our collection of cocker spaniel images and even a collection of cockadoodle images. And we can even create a function that's fitted to map these such that we could determine whether something was a poodle, a cocker spaniel, or even a cockadoodle. What happens, however, when we introduce mutts into the problem space? Mutts are a collection of a variety of different types of breeds of dogs, be they poodles, cockadoodles, cocker spaniels, etc. And the distribution for mutts makes it such that it becomes very, very complex. Put another way, non-distributed representations start breaking down where there's a lot of variation of the data in the form of, say, mutts, noise, or other things. To address the curse of dimensionality, a new type of data representation needs to be used, one associated with deep learning. This type of data representation is known as a distributed representation, where the strategy is to break up a space into regions such that there are shared attributes between different concepts in these regions. Well, what does this mean? Imagine again we have our collection of poodle images, our collection of cocker spaniel images, our collection of cockadoodle images, and our collection of mud images. Using deep learning, we can basically, as a statistical matter, identify shared attributes between these different regions, different breeds, and generalize the same. So we can effectively extract common attributes such as snout, ear, tail, even curly fur, and know that the collection of these will result in a representation of a dog. So the approach under a distributed representation of data is one where common attributes are learned and a function is fitted to these attributes to render a classification decision. Let me give you an example of this. Imagine again we have our poodle images, our cocker spaniel images, our cockadoodle images, and our mud images. Well, what we can do is we can create a function from these images and then pass in a cockadoodle image to this function and then get a resulting decision as to whether or not the image is of a cockadoodle or not. Now that we discussed a distributed representation of data, we're ready to look at the Universal Approximation Theorem. The Universal Approximation Theorem states, in other words, single hidden layer feedforward networks can approximate any measurable function arbitrarily well, regardless of the continuous non-constant function used, regardless of the dimension of the input space, and regardless of the input space environment. In this precise and satisfying sense, feedforward networks are universal approximators. Let me give you an example of what this means. Imagine you have a deep learning network and a data distribution. You can traverse through a portion of this deep learning network to create a portion of the fitted function. You can traverse again and create a further portion of the fitted function, and you can do a final traversal to create the final fitted function, as a result of which you can make a classification decision. Really, the approach here is that simple functions used to identify simple data attributes can be used to build more complex functions fitted to the data to identify more complex attributes. Put another way, you can basically identify nose, ear, curly fur to generate and then identify a more complex attribute such as dog. When the theorem describes a single hidden layer feedforward network, what does this mean? It means a deep learning network with 3 or more layers. Further, when the theorem states regardless of the continuous function used, what does that mean? It really means that so long as the individual functions, where each function is associated with a node in the deep learning network, can collectively represent a continuous series of data points, the deep learning network can create a function to approximate most any space. Further, when the theorem discusses or states regardless of the dimension of the input space R, what does that mean? It means that no matter the complexity of the space, even if it's comprised of poodles, cockadoodles, cocker spaniels, and mutts, a deep learning network can create a function to approximate this space. Summing it up, deep learning views the world as a collection of continuous data approximations as opposed to the traditional approach, which views the world as a collection of true or false propositions. The traditional approach, as embodied in the non-distributed representation of data, does not generalize well and breaks down in complex spaces. Distributed representations of data, as implemented in a deep learning network, abstract and generalize common attributes from the data. The Universal Approximation Function Theorem states that a deep learning network can create a function to approximate, fit, and represent the data in any continuous problem space, no matter the complexity. I hope you've enjoyed this presentation.